Hi, everyone, and welcome. My name is Sandhya Simhan. I'm the Director of Marketing here at deeplearning.ai. Welcome to our event series, AI Access. If you'd like to check out our previous event on integrating design and technical innovation in AI-first products, you can find the recording link in the description box. Machine learning represents a powerful set of tools and techniques to make sense of complex problem domains and challenging problems. But despite its power, it's rarely the whole solution to a challenge. To explore a set of those challenges and demonstrate how machine learning, distributed data engineering, and a product-oriented mindset can result in impactful results, we are excited to have Zachary Haniff, the Senior Director of Machine Learning at Capital One, join us today. Currently focused on leading teams to develop transformative platforms, data, and analytic capabilities for Capital One's card business, Zachary is passionate about modern analytics and the infrastructure and platforms supporting and democratizing them. Before Capital One, he developed analytics and capabilities to secure and protect enterprises and consumers, focusing on cybersecurity, fraud, and anti-money laundering. Before inviting Zach to the stage, a friendly reminder for our audience who have registered the Slido ticket, don't forget to log into our Slido page to submit your questions or upvote others. You'll find the Slido access link in the reminder emails we sent you. And now, without further ado, let's welcome Zach.
Hi, everyone. Thank you.
Hi, Zach. Hi, thank you for joining us today.
Well, thank you for having me.
Before you start your oh, I'm sorry, it seems there's a little lag. Thank you for joining us today. Before you start your presentation, I'd love to do a little quick 3-question lightning round so the audience can get a few insights on how you've built your career in AI. So first off, how did you get started?
So I got started really a very long time ago while I was still in my undergraduate, doing my undergraduate degree. I got involved with data and analytics as applied to cybersecurity, and I loved every second of that. And it just kind of built up from there.
Awesome. Next, how do you and your team stay up to date with frequently changing machine learning techniques?
I think everyone has a different way of doing this. Some people really like asynchronous learning, so picking up papers, journals, things that they are capable of reading. Some take a more formalized approach, taking courses either online or in person. And other groups do it purely through kind of the act of working on material and the act of experimentation. Working with the technology in and of itself, playing with it, turning it into a game is some of the best ways to learn. So I think everyone's always got a little bit of a different approach. Myself, I do a lot of reading.
Sounds good. Different modes of learning for different learners.
Very much.
And last but not least, what is some of the best advice you've received as a young machine learning engineer over the course of your career that you'd like to share with our attendees today?
I think it's that you shouldn't be afraid to fail, right? And that's interesting advice, because I think for much of our lifestyle, especially today, we're told that failure is inherently terrible and inherently bad. And I think that kind of loses a little bit of the beauty of computer science and a lot of the work that we do in this industry, which is we are an experimental science. We try stuff and sometimes it even works, and that's great. Now, don't get me wrong. I don't think you should fail for the sake of failing either. And you want to, manage all of that, all the real world considerations there. But I think there's a real value in not being afraid to try something and fail. And that can just lower the friction to trying experiments, trying new things, talking with people, and then learning from those experiences.
There's a great quote that I'm forgetting who said, but it's that we often forget that computer science is a science, that it is inherently a game of, hypotheses, research, hypotheses, testing, validation, and then repeating. So I think, it's a good thing for most machine learning engineers and aspiring machine learning practitioners to keep in mind.
Yes.
Now we'll go ahead to your presentation. The stage is all yours.
Fantastic. Hopefully I'm able to share the screen here and nothing goes sideways on me. There's always something weird about technology when you do that. So everyone, thank you for coming today. The title of the talk is Advanced Analytics from End to End. Introductions are always a little awkward for me. And so one of the things I've always done when giving talks is try to start with this one particular story. When I was doing my undergrad, I had a mathematics teacher who taught combinatorics. And on the first day, the professor entered the room, placed a pack of markers on the table, and said with the kind of conviction most people reserve for talking about things like gravity and physics, that I am here on Earth to teach mathematics. And by way of introduction, that kind of a statement has stuck with me ever since. And so in the more local sense here, my entire career has revolved around collecting, working with, and managing data, performing analytics, performing systems that utilize it, that collect it, that work on it, that sort and organize it, and make those insights available to some kind of end user. I have focused primarily on machine learning based analytics throughout my career, but I wouldn't say that that has been the sum total of it, because as I will get into over the course of this talk, as you try to bring machine learning into a production environment, make it a part of a product, do something with it that is able to affect the world in a positive way, you need to work with the stuff around it too. And so I'm currently at Capital One. I'm working on production considerations of things like data models, feature computation inside of our card line of business. I have been focusing for a couple of years now on bringing machine learning capabilities into the market. And so for a little bit, and this is a little bit of a change in my recent career path, instead of focusing on development time considerations, which is what the majority of my career has been focused on, I've been recently almost exclusively focused on the production side of the life cycle. And previous to coming here, as you know, was said a little bit earlier, I led teams inside of Capital One and in other places to build transformative machine learning capabilities from beginning to end, from design time to productionalization. And I particularly have enjoyed my work inside of adversarial domains. I'd like to think that I've learned some things worth sharing, and hopefully I'll be able to talk about them today. I'll warn everyone that I do write really dense slides, so it turns into a little bit of an eye test. It's for the benefit of future participants who might not have the benefit of either time or audio. I know some people in even some of my learning groups watch YouTube presentations of talks at very accelerated speed so they can see the slides and how people react. So this is kind of based off of that. Should be a lot of fun. Before we get started, I've got one disclaimer that I have to make. My experiences, all of our experiences are all different, and it's moderated by the context around the problems that you're solving, the culture and technical expertise around your problem, and that's present in your company and industry. Kind of the temporal effects, you know, when are you solving this problem when you are looking at it based on where everyone else is around you. And so while I hope that some of my experiences can help you in your own endeavors, and I'd like to think they generalize well, please don't think for a moment that I'm standing up here saying this is the objective truth in all situations, because nothing could be further from reality. And then two, I try to avoid talking too much about specific technologies, but when I do, I'd ask everyone watching this now or in the future to remember that they're not advocations by Capital One, who is my current employer. Anything that I'm talking about is really just a mention of my personal experience and opinions. And honestly, you can apply that statement to pretty much everything in this talk. It is an amalgamation of lessons that I've learned over the course of many companies, many domains, many problems, many challenges. And so not something that should be interpreted as, oh, hey, this is exactly what Zach's current employer is doing. So great. Let's start with kind of the first statement that I have, which is the context in which you are solving problems will inform everything you do from your initial design conversations all the way to production. My experience has been in applied machine learning. I am not like many of the luminaries in our field who are developing new theorems, who are proving direct branches of mathematics applicable to machine learning. I apply those lessons that they have learned, developed, and have shared with the rest of the community. I am not directly a theoretician myself. And so as a result, I think of everything from the perspective of developing it to solve a discrete problem or a set of problems, applying that in a product or service, and bringing that service to an environment where it can leverage itself against the challenges at hand. And so there's kind of three things there that kind of distill the lessons that I've learned, or at least several of the lessons that I've learned in doing so over the course of my career. It is that one, analytics and machine learning does not happen in a vacuum. You need to understand your domain-specific assumptions, failure conditions, and responses. That two, when building your analytic capabilities, developers should have joint teams by skill set. So that means you're pairing statisticians, data scientists, machine learning engineers, software engineers, designers, modelers, all of it together whenever possible, and that you're able to ensure that they're engaged throughout the entirety of the development lifecycle. I've had interesting experiences in worlds where you have one group of people, like say software engineers, build a system and then kind of throw it over a wall to the data scientists or modeling teams, and then kind of walk away and never talk about that again. I don't think that's a great methodology. I like seeing teams and I like working on teams where you have joint skill sets together, because you get a lot more than the sum of the parts when everyone is working on the same problems, or at least has direct visibility into it. And finally, three, I strongly advocate teams going through their own machine learning lifecycle, building machine learning teams or working on a product using machine learning, to not only focus on the algorithm, but to invest heavily in infrastructure, data, and interfaces. And if you're going into production, if you're building a product or service, I almost advocate that you invest in those three things in that order. And I advocate to teams to be very, very deliberate in what you build into your pipeline and your product and what work you take on. I think overall that as modeling teams mature, they will move from artisanal modeling output, effectively, hey, we've worked on one model and that's the thing that goes out, to a world of productionalized capabilities, effectively where you're building these things instead of at artisanal scales, at industrial scales. I think the industry as a whole is seeing energy transition in this direction, making machine learning work scale dramatically. And I think we're seeing this huge wave of technologies that concern themselves with the infrastructure around modeling capabilities. I am super excited about all of this, particularly the idea of infrastructure supporting machine learning, because it empowers automation, it lowers debt, both technical and business, and it speeds development. I think it's critical for our field to grow to the next maturity level, and I'm really glad to be here today to talk about at least just a little sliver of a fraction of that. Saying all that more simply, understand your problem domain and how it affects and is affected by your analytic capabilities in your surrounding product and/or pipelines. Control for debt by building teams that represent multiple skill sets, specialties, and domain experiences. And then finally, when spending your energy and resources, you will get a great return on investment if you invest in your infrastructure, data, and interfaces. And I would say in a biased way, before anything else. All this varies based on domain context, but it's a pretty decent rule of thumb that's served me well so far. Model developers, I have found, and development teams focused on models feel often like they've got to consider a large number of variables directly. And so they feel that things in the machine learning set of machine learning concerns are things from efficacy and algorithmic considerations to considerations like data access, how to serve the thing, what their control planes are, and how to deal with monitoring of the system on the whole. And that feels overwhelming for teams, especially when they're first starting. I think, however, that it is easy to lose sight of the fact that machine learning teams are often a small piece of a much larger whole. I've stolen this from the paper Hidden Technical Debt in Machine Learning, which is fantastic. And I actually think it encapsulates really, really well kind of my philosophy here. Your machine learning code, the statistical artifacts you build, the models that you create, are really one small component in the entirety of the pipeline that governs what you're capable of doing and how you're able to continue moving forward and serve your capability in a scalable, efficient sense. And if you leverage those things around you, you will save yourself a lot of time and energy and radically reduce technical debt. Applied analytics are affected by their domain context, as are the systems around them. Let's make things a little bit more concrete. A lot of my modeling experience comes from working in adversarial domains, or domains where, as your model improves, there's some other force out there that is capable of interacting with and responding to your model. It's kind of similar to the Red Queen's race, which is an analogy that's used inside of Lewis Carroll's Alice in Wonderland or Through the Looking Glass. And there's a quote in it that says, it takes all the running you can do to keep in the same place. And in an adversarial domain, that's very true. Think about it from the perspective of cybersecurity. As you, a defender, gets better, your adversary, the attacker, is heavily incentivized to react in response to you, try new things, find new exposed surface area, and evolve their approach to try and evade your ability to detect them or stop them. And we see this in a lot of fields where machine learning is being applied today. Cybersecurity, fraud, kind of any environment where there's someone you're able to, where you're trying to avoid a particular behavior or de-escalate risk, where that risk is being driven by human activity, is a really clear example of this. And one of the things that I'll say here is that machine learning might not be necessary to perform in these spaces. We certainly did all these things before machine learning was a tractable system of approach for much of this. But machine learning brings huge piles of benefits to be able to consider high dimensional data and adapt to change. These domain requirements inform your product and therefore the model itself. So let's talk about cyber network defense for a second. You've got to defend an unknown number of services with unknown vulnerabilities against unknown attackers while still supporting your users' needs, especially if you're trying to do this in an environment that is already up and running. Like, for example, an environment inside of a large enterprise that exists today. You have to work in concert with human analysts and responders because the insights that you're able to generate need to be acted on, and most cybersecurity organizations staff their team with humans. And then finally, your adversary is incentivized to react to your efforts with speed and find gaps in efficacy that can lead to, let's just call it, a materially worse user experience. If your model is trained in a vacuum, some of these concerns might not be clear. If you simply train your model off of like a static data set that someone provides to you with no external context, you will probably end up with a model that performs well on that data set. And you will probably also end up with a model that does not accurately or well represent the world that it would be applied against. And these considerations are really important. Obviously, those considerations are things that are the clear challenges. You need to have something that changes quickly. You need to be able to filter boundaries and events inside and outside of the model. Your design considerations need to consider the human experience from the outset. For example, how many alerts is too many or too few, and how do you want to engage those humans? And your model adjustments should probably be automated if possible, especially if you're in an adversarial space that changes quickly or dynamically. And so you can make learning your domain-specific context a part of your model's goals, or you can ensure that your non-modeling functionality is domain-aware and is capable of enumerating things like failure scenarios. And that brings me kind of the next layer down here. When talking about your domains and how your domain-specific qualities are important to designing your model, one of the things that I encourage teams to think very hard about that I have seen teams sometimes forget are your failure conditions and your response to those failures. There are failure conditions within any analytic capacity. At some point, malformed, malicious, or irrational input will find its way into your pipeline. Not all analytic capabilities can be local, and network partitions will help happen to the best of us. Upstream and downstream, partners can exhibit strange or non-compliant behavior because in many organizations, especially larger ones, the pipeline is not a isolated system unto itself. It depends on myriads of other systems and other teams that are all operating on their own operational cadences and have differing SLAs. Your system could expose patterns that habituate users to a particular behavior, and a future change that you build in could break that workflow. Or worse yet, your partner services are not perfectly aligned with your release cycle, and changes might be not upwards or backwards compatible, especially if there's some kind of intent breakdown. And these challenges are present in systems of all sizes, but failure conditions don't scale linearly. And you need to consider how your system is likely to fail, what your possible breakpoints are, and most importantly, how you will respond in those situations. And the goal is to ensure that failures are infrequent and failure responses are aligned with domain needs. And that's why this is really important. I think I've seen teams, when they start thinking about failure scenarios, think about it in a domain agnostic way. What happens if the service goes down? Well, we'll send an alert, we'll restart the service, we'll perform auto scaling. It's a very technical based approach. But if you think about that, that's really only one slice of that pie. It's only one part of the overall scope on the whole. I think that there's an element where you want to be able to think about what do we change in the event that there's a technical failure, and what do we change in the event that there's a domain failure. And so graceful failure environments look like this, where an elevator has broken, and an escalator has broken and it's temporarily turned into stairs. And not quite as much like this, which is a tweet that went around earlier this week, where an individual named Rachel True posted a screenshot saying, hey, I've been having trouble with Apple iCloud because of my last name, which is an input variable problem. And I don't mean to call out Apple here by any stretch of the imagination. It's just something that kind of was topical and came up recently over the course of the last, kind of 48 hours kind of idea. And it demonstrates one thing. It's hard from a software perspective to think about what happens when your systems fail. And the introduction of complex domains and complex models can cause failure to occur in more subtle but no less meaningful ways. And that increases the importance that I think individuals and teams have on building out infrastructure that lets them monitor for failure, respond to failure, anticipate failures, and most importantly, rationalize about those failures inside of environments that might be both technical, as we're seeing in this screenshot, and domain specific, where failure is a word that is defined based on particular constraints inside of the domain at question. So the question is, how do you do that in a practical sense? As your system gets more complex, this obviously gets harder. And I've referenced domain failures here a couple of times, and that's where it gets really tricky, especially in the area of machine learning. Incorrectly calculated input features, for example, can lead to correct operation. No system has crashed, no error screen displays. Everything from a technical perspective continues to work appropriately, but it can still have dramatically different decisioning outcomes, right? If your input data is bad, your output data is probably going to get a little weird too. And an example of this can be very trivial. Let's say, for example, you have some kind of classifier that takes as input data the height of the individual who is interacting with the system. If you've historically been measuring that height in inches, and suddenly someone provides you that height in centimeters, you've obviously entered into a scenario where there's going to be a model failure, where your model is going to give weird-looking input because you've suddenly changed the boundary conditions under which it must make a decision. And so how do these concerns enter into the system? They can be introduced during handovers between teams with differing skill sets. They can be introduced when teams turn over or change between and therefore lose local knowledge. They can be introduced at boundaries between interconnected system components, and failure conditions compound as the total state that developers need to consider exceed the collective knowledge and experience. I think we've all probably worked with models, or at least systems, that are so large and so complex, no one person can think of the entirety of that workflow all at the same time. And that's when stuff can start to creep in passively that can lead to situations where a user might be might think to enter in their height in centimeters instead of inches. They might be allowed to do so, or at the very least, that isn't detected. An investment of infrastructure, I feel, can form the guardrails that allow you to scale and remain robust to change without increasing your overall cognitive load. Infrastructure is a really tricky topic, especially these days. It's unlikely to win any major awards by itself. And with apologies to Randall Munroe, that's kind of why we're here today. That bookkeeping, the things that allow you to offload, I'm going to call it tedious work, to make sure that you're able to do things more safely, more securely, and without having to worry about, did you kind of like not carry the one in performing some series of complex operations. The goal of infrastructure is to enable repeatability across the pipeline and reduce efforts for adjusting components of that flow. You want to look for robustness to change. Your data is messy, your problem is evolving, and guardrails let you iterate faster because you're not paying attention to what often can become a Rube Goldberg machine of a pipeline. 3 years ago, I gave a talk very similar to this that talked about kind of the ways that certain teams inside of the company I was working at were responding to the reproducibility crisis in science. This is a picture I stole from Nature that discusses this as science as a whole. So biology, chemistry, physics, all of it. But I don't think we're immune to the reproducibility crisis. I think there's probably a lot of us who have tried to reproduce a paper that's been published and have had challenges in doing so because the paper leaves out steps, the data is hard to access, it's hard to be able to reproduce things even in a field that's so easy to join in and participate in as computer science. And without reproducibility, what kind of a science do we have? The point of science is you test ideas by experiment, which means you need to be able to repeat them. And so we thought at the time that we wanted humans focusing more on determining if their models were good as opposed to the raw act of generating them in and of themselves. Very recently, Capital One publicly released on GitHub a system called Rubicon, which is kind of an answer to that case. This really talented, really amazing team built this system to make it really easy and trivial to store and retrieve model inputs, outputs, and analyses to file systems, either local or S3 or other stores of truth that allows you to kind of enforce and agree with best practices to make sure that you can log every single experiment that you did. And it's kind of an example of a piece of infrastructure that makes the overall process of model development safer and easier. And now this is certainly at development time, and there are implications going into production. But I started this talk by saying there's a lot of production areas that I wanted to talk about today. So let's see some of those other areas that infrastructure can improve. I think that the industry as a whole and the community around open source inside of machine learning is reducing a lot of that friction going from dev to prod. But prod considerations are distinct from development design requirements when we're talking about supporting infrastructure. Latency enters into the picture in ways that it didn't for a developer. Certainly you want, during model development, your system to be snappy and responsive and not introduce friction as you build and develop things. But you definitely also realize very quickly that, hey, during the act of model development, latency, for example, a 3 millisecond SLA that you might have with a customer is not as immediately important. And so it can be forgotten about, or a secondary consideration that you don't remember until later on in the process. Iterative flexibility inside of production is not quite as necessary. Data access patterns and systems may well change depending on where you are and the kind of environment that you have. Monitoring becomes a more diverse effort because you've got a larger set of things to monitor and keep an eye on. And then finally, input validation and recovery definitely has to be performed. Production deployments sacrifice flexibility for performance and efficiency is the statement that I would make. And I'm sure there's someone in the audience who is aching to be able to raise their hand and say, hey, I disagree with that. I live in a world where my production environment is just as flexible as my development one. Those certainly do exist. That's probably very true. But I would say that it's not the standard case across all organizations, because many organizations, due to the fact that industrial scale machine learning is kind of an emerging discipline, not everyone has made it down that maturity curve yet. And so there's lots of tools that are available to make model serving easier. We're putting a lot of energy around that as an industry and decreasing the friction in the promotion process from dev to prod. But there are fewer systems that are available to ensure that you have ongoing things like data quality, well-managed feature orchestration, and other things like that inside of a heterogeneous environment. Data quality is critical, and it's deeply embedded. Inside of your domain, you've got something that is a constraint that can be evidenced by your data, but is not necessarily inherent within it. And so the thing that I ask everyone to take away from this talk is this: do not trust your data. It will sooner or later lie to you. And if you're in an adversarial environment, like say cybersecurity, it will do that intentionally. You're likely to rely on data for a sufficiently complex model or a sufficiently complex process which your model is a part of, is to turn around and ensure that you've got the way to you have a way to handle data of differing quality levels that you might not have direct control over. Data quality covers a kind of a wide number of dimensions. 5 that are really well known and well understood are up here. I won't read through all of them because that gets tedious very quickly, and I don't want to bore everyone. That's why I create the dense slides. But they are accuracy, completeness, consistency, and timeliness, and validity. And then finally, you have two more, which I have found show up in production environments. Pervasiveness, which is how often do we duplicate the same data in multiple places, and temporal mutability, which is to what extent does the data describe a phenomenon that naturally drifts over time, and where are we accounting for that drift? I think that last one's really important. There are multiple definitions of the same thing in many cases that can be difficult to manage in an effective way, and this starts to begin a discussion on the concept of lineage. Lineage records things like the origin of data, where it's been used, where it's been stored, and how it's been modified over time, and it's hard. It's easy to talk about, it's easy to express, and like reality, as you get deeper and deeper into it, there's even more detail. Reality is really detailed as you get down into it, and that's really hard to do, especially if you don't have a fully unified, super well managed, almost monolithic data control environment. But that is a different talk entirely. Here's an example of a data quality check that will hopefully give an example of why this can be so difficult. And as you look at this, I would say recall to the fact that many systems, especially systems that don't do feature learning on their own, can take in high dimensional data, and as a result, need to perform operations that are similar to this on tens, dozens, hundreds, if not thousands of individual fields. So let's look at the United States Social Security number, which can be used as an input for one reason or another. Now, please don't get me wrong here. You would never want to use a Social Security number as direct line input to a machine learning model. There's nothing in there that's meaningful to learn from. I'm giving an example of a data quality check, something that we should be able to grapple with pretty easily in the span of however long I have on this slide, to be able to talk about for a concept that most people should be able to recognize. Effectively, how do you recognize a taxpayer inside of a country? So let's think about this. And again, don't use Social Security number as an input to a model. Bad idea. So a Social Security number is a 9-digit number that's issued to U.S. citizens, permanent residents, and a couple of other different classes of citizenry inside of the United States. And that feels really clear. There's government regulation on it. It's published publicly. There's a lot of standards. And so you look into it and you realize that a SSN is a 9-digit number in the format of 3 A's, or 3 digits, then 2 digits, and then 4 digits at the end. And so somebody looking to make sure, hey, if there's a human who's typing in Social Security numbers, let's make sure they didn't type it in incorrectly, could very naively simply say, hey, I'm looking for 9 digits separated by dashes that fits this format. Cool. And then you look into it a little bit more and you realize that those 3 A's are a geographic area number. They represent a specific area of geography in the United States. The 2 digits in the middle is the group number, which has a little bit more entropy in it, but still isn't truly random. And then your last 4 are the serial number, which is the main source of entropy. So these numbers could probably be validated easily. They're generated with an algorithm. So a less naive system doesn't just look for 9 digits. It looks for 9 digits and specific combinations of things like the geographic number and the group number. And that helps you prevent at least some series of typos. But on June 25th in 2011, that changed and it became almost completely random. It removed the geographic significance of the first 3 digits, and it eliminated the significance of the group numbers as well for many groups. And previously unassigned area numbers were introduced because there was another requirement I didn't mention earlier, which was that area numbers like 000, 666, and 900 through 999 weren't valid for assignment. And so that new generation scheme brings us to the concept of an external validator. Like, for example, the Social Security Administration publishes a validator that says, hey, is this truly a valid Social Security number? Submit it to us and we'll tell you. It's an important government service. And that brings us back to our failure conditions again, which might introduce a new one, secondary service failures. What happens if your validator is down? What happens if there's a network partition? What happens when you're given an invalid Social Security number and you need to act on that in some way, even before it makes it to your model, or the data that is collected with it makes it to your model? External validation introduces new operational constraints, things like rate limiting, reliability, and failback, and you're going to have to wrestle with them at some point or another, depending on your domain, but I would wager that almost all do. And none of this addresses things like temporal complexities. Are we doing this in real time, batch, or streaming? All of that complicates things. Thinking about this and the domain as a whole can get very complicated after a while and is very important. And data quality validation is hard. That was a really simple example. Many rules can be dealt with in a handful of ways, and it's a fairly well-known example of how do you validate a piece of data that has hidden meaning inside of it. And so it's easy at first glance and gets more difficult in practice. And in some domains, your data is outright rewarded for lying to you. I stole the image on the side, the rules of perf that I think are posted inside of Dropbox somewhere. At least there's a picture on the internet that claims they are. And I really like them because the same things that you have to think about for performance are very relevant inside of production environments where you have to perform actions multiple times. How do you speed things up in production as opposed to development? We have SLAs and all sorts of other complexities that we have to think about and consider. And that directly ties to user experience. So you build a pipeline. You've got some set of data sources. They feed into some kind of feature generation if you're creating features for a machine learning model. Sometimes there's secondary stage operations, like, for example, user validation for like a user lookup or something like that, that feeds into yet another form of feature generation. And then both of these bodies of features feed into a decisioning model. So you've got a pipeline. Your model is a component of a larger mechanism, and upstream actions can have these really wide-reaching downstream effects. And you can try to do things like corporate-wide synchronized testing and releases, but that's not practical. And it's something that can be really hard to manage because you effectively have these big stop-the-world functions. And I advocate to people that when they're building machine learning systems and they're building pipelines around them, no component should blindly trust data that it gets from something else. Consumers of data should not trust that their upstream has done their due diligence. Producers of data should not assume that consumers will necessarily do theirs. And while, of course, producers can't know all of the use cases that someone downstream is going to use their data for, they can at very least make sure they can address all the considerations that they know at the time and surface and make visible what things they're already looking at and how they're dealing with it. This actually gets harder if you're an established company as opposed to a brand new one, because you probably have legacy systems or currently existing ones that don't always play nice with each other or don't necessarily adapt well to change. And so investing in some of that infrastructure early on, if you have the ability to, or if you're able to influence other teams to, investing in infrastructure that validates data quality and business applicability of your data before it makes it to your model or before it makes it to secondary downstream decisioning or analytics components is really important, especially if you have to find ways to get that infrastructure in to deal with messy data that might exist inside of systems that you can't necessarily directly influence or change. That feature problem extends directly into production. Your features are data, and how do they get represented? One of the things I really advocate for is for teams to be able to turn around and put their features into data lakes. That way you're adding to the body of data that your organization is capable of working with and learning from. The raw data you started working with, the transformed data, the derived data, the features that you actually applied. It also helps with monitoring and making sure your system's doing what you think it's doing. So you're able to turn around and identify, hey, this is something we can work with. This is what we did. This is how we came to this choice. That leads to another problem that I think teams should be thinking about and building infrastructure around. How do you deconflict with features? Sufficiently large organizations will eventually create transformations for raw data to generate features that are duplicative and probably maintained by teams who have never spoken to each other or never identified each other. And that's pretty interesting. Some teams, if we go back to our social security number example, would be able to turn around and say, hey, some teams are just simply validating that it's a 9-digit number. Other teams perform the full algorithmic check or call out to an external validator to make sure that that works. And so just like your model, feature generation has very real performance and scalability considerations that need to be addressed in production environments. There's data considerations too, because this all becomes a larger orchestration challenge. A couple other sources of debt that I think teams who are building infrastructure should be thinking about and make sure that they're able to operate with. First, configuration. Configuration should be easily monitored, tracked, and validated with accompanying change logs, and hopefully stored and modified in as few places as possible with documentation that supports it. And in this age of YAML everywhere, if you've ever configured a Kubernetes system, you've dealt with this, should be treated with the same rigor as your source code, data, and other critical components. I think the same thing's true for your dependency management. If you're a machine learning team, your dependency isn't just your upstream systems or the source code you're working with or supporting libraries and infrastructure. It's the data itself. This gets back to lineage. And I think that one of the things we've identified as an industry, and it's starting to be solved, is while there are many tools to perform dependency analysis for things like source code, the same can't necessarily be said, until recently, for validating data access in non-managed environments, which is the environment that many organizations operate in. You want to have lots of rigor around your development, code, and promotion. And I think there's a bunch of infrastructure there, particularly inside of things like ML flow that do a really great job for it. And I think that teams really need to be thinking very, very deeply, calling back to our domain-specific reasoning discussion at the very beginning of this talk. How do they identify metrics of efficacy so they don't define those poorly? Speed to market's a really great example here. It's a great metric, but if you're measuring it at the detail level of how quickly can I get another model out the door, that's probably not super helpful. You want to have metrics that are detailed enough to identify weak points and potential areas for improvement. Here's the kind of punchline here. I think that there are really great things that are results of investment. Infrastructure can often eat last, and it's hard to convince upper management in certain situations that it's as important as the model or the analytic in and of itself. And so there's definitely a sales point in here that teams need to be doing to make sure that people can be excited about it and acknowledge the need. No one gets excited about roads in general. And I encourage you to have those hard conversations anyway. By investing in this, and this is the big punchline, I think, new intent becomes faster to implement because teams spend less time worrying about whether or not they've added new intent that has broken something else. Things get safer. Your overall velocity increases, and that's really important. And this can feel very daunting because there's a lot of concerns. And if you're at the beginning of your respective journey, that can feel scary. But I encourage teams who might be listening to this now or in the future to try going down it anyway. Any little bit of progress that you're able to make to take mental burden off of your developers will lead to good effect. The good news is that this is getting easier. Two systems that I've worked with recently that do this are TensorFlow, which is building a very robust suite of capabilities for that kind of development, production, and promotion lifecycle is very meaningful. And there's all sorts of things in there for validating your input data, checking statistics, and performing schema generation, all the way to model monitoring. There's also a great project written in Python called Great Expectations, which makes, certainly at development time and to some degree at production time, depending on your temporal needs, makes doing data validation really easy, especially if you're looking for statistical relevancy or things that can be expressed in a relatively simplistic way, and they make it really easy for people to work with. Two things that I've worked with recently in personal experience that I think are really cool. I think, though, that while the future is getting closer, it is still not distributed evenly. There's a lot of energy going into that black box, making the modeling lifecycle faster. There's 5 different deep learning frameworks that are out and available right now, relatively few things for doing data management. And it feels to me, this is one man's opinion, that the targets for these systems can lead to disparate knowledge. And I think that's something we want to be very aware of. Finally, I think that joint teams are valuable and they have their own challenges. Everything I've said so far today becomes a lot easier if your modelers and your software engineers, your data scientists are all working together because they will see things that the other groups don't. But joint teams have challenges. Team members can have heterogeneous knowledge and experience, which increases the burden on managers to have communications, to discuss and communicate intent, understand results, and report progress. And that might need to be written or sent multiple times to reflect the domain experience and priorities of these individual groups. That being said, knocking down silos can be easier if these skill sets are together, but it still needs to be done. And I still advocate for having joint teams because communication does become easier overall. Everyone's getting the same message. And in time, this actually becomes a lot easier. There's probably a learning curve for managers who haven't done this sort of thing before. But I think that it ends up avoiding a lot of technical debt and business debt during model and system development. It also makes sure that infrastructure creation is well aligned with team needs because everyone can see it and contribute. To close out, because I know I'm coming right up on the end of my kind of time here before we get to the questions, I think a lot of this is known. I don't think there's really much in here that I've said today that most of the practitioners here, especially the experienced ones, don't already know about. But it's easy to forget or ignore this during active development. It's easy to kind of start making progress on a project and forget a lot about infrastructure because it can be difficult, it can be hard, and it's something that you have to grapple with. And I encourage teams to kind of remember those 3 things, right? First, you're modeling a domain. Don't forget your domain considerations as you build your model, as you build your infrastructure, and you build your system behind it that allows it to come to production and make transformative change. I think two, that if you're building infrastructure, and I think you should, remember you're building a platform. In the long run, your infrastructure should be something people are able to build on top of and alongside of. The more you put your use case, your intent, your particular business purpose, logic into that infrastructure, the less transferable it is to other groups. And infrastructure is one of those heritage things. Once it's been built, if it's easily transformable, you're able to kind of jump in and engage with directly. And I think that there's a lot of interesting stuff here that people can kind of jump in and engage with. These considerations are broad, they're complex, and they're interconnected. And again, I encourage you to have joint teams that can manage that state space. One guy by himself is probably not enough, especially if you're doing this at a large scale. If you're a solo founder or a really small company, many of these lessons are things I think you should be thinking about in the future, but your particular business requirements might say, hey, we're taking on that technical debt. Technical debt is a choice. I'm trying to encourage you to be in a space where when you decide to pay off that debt or you take it on, it's a more deliberate choice than it can be for many teams today. It's all achievable. It takes time, energy, and this can be hard, advocation to other groups or leadership, but I believe it delivers tremendous long-term benefits. I think I've just barely exceeded the time that I had for the talk in and of itself. I think we've got something on the order of maybe 15 or 20 minutes to answer questions. I am super happy to do so. I'm going to take a look over here, or hopefully some of our moderators from Deep Learning AI can tell me how we're going to play this thing out.
Sounds good. Thank you so much, Zach. This was really fascinating. I love, there's a ton of nuggets that I loved in it. The one that I am most thinking about right now is actually the letter that's going out in the batch this week. So tomorrow's letter, batch letter, is actually about the necessity for communication amongst teams.
Yes.
So very timely moment as we're thinking about it. Like it's a critical skill. Even beyond just the technical aspects. And quite honestly, what you said about, it's almost like it's not, the infrastructure is not the sexy part of what people think of when they think of machine learning, but it's one of these things, it's like it can be your secret power. And so I really love both of those nuggets. So we're actually gonna go ahead and dive into the questions because our audience is bubbling with a ton of questions on Slido right now. So we'll go ahead with the first one from Chris Fortes. You have 2 degrees in computer science. When you hire, what's your take on formal degrees versus online courses, say from Deep Learning or others?
So, excuse me. I think there's multiple phases in anyone's career. And because I advocate really strongly for hiring joint teams, the expectation that I think hiring managers who are building joint teams have will differ based on your skill set. If you need a deep, a very strong, a deep machine learning expert who really has a deep command of theory, you're probably more likely to find what you're looking for inside of someone who has at least 1 degree. Let's just say that, right? That is in no way, shape, or form meant to say that there are no autodidacts, people who teach themselves, that there's no way for you to get into it if you don't have a PhD. I'm not making a statement that it has to be a bachelor's, master's, PhD, anything along there. I'm just simply saying that if you're looking for a particular skill set, there are definitely degrees and paths that people take to get to that skill set that they self-select for. So I would say there's probably a little bit of like, you're more, if you're going fishing for talent, fishing in certain pools might be more likely to get you the talent you're looking for. But I think managers who keep open minds, who look at things from a portfolio basis, who understand that there are different paths that people have coming to the art and science as a whole, and especially who are building joint teams are really important. If you're building a machine learning team and you've got 2 software engineers who don't have any specific formal training in machine learning, deep learning, anything along those lines, and one has been taking a lot of courses inside of like online courses or self-learning or anything along those lines, has a portfolio of work, I think managers should understand, take a look at that, and consider that in their evaluation as a part of the normal interview process.
No, that's a really fantastic point.
One man's opinion.
No, it's actually ours as well. I mean, on our website, we talk about the fact, on our homepage, in fact, you can go look it up. We talk about the fact that technical knowledge isn't everything. And I realize this sounds really weird as, head of marketing for deep learning for me to say this, but the reality is an AI career requires technical knowledge. It requires practical experience, hands-on experience, whether that's the form of portfolio work or something else. And it also requires, quite frankly, a network of peers, of people that when you get stuck, that you can go to. Like that's a sort of unrecognized aspect of what you get. Now, whether you get that through a traditional university system, whether you get that through, brands like Deep Learning that do education in other manners, like there's tons of ways to do that. We try to build our community in our own way through events like these and so on. But it's one of those critical things, like, like book knowledge, as I call it, only gets you so far. It's the practical knowledge and the connections that really make a career out of a degree.
I think that's true. And it's what are you trying to do? What role are you applying for, right?
Mm-hmm.
Where are you trying to go with it?
Yeah.
Limiting yourself is interesting. Like, it's probably not a great choice. Continual learning, if you're a technologist, that is the name of the game.
Yep, for sure. It's actually funny, when I joined day one of deep learning, I actually knew zero about machine learning, absolutely nothing. I never touched Python in my life. I'm able to have conversations now, partially because I host a lot of these events and I'm involved with technologists, but also because, even without knowing the math, even without necessarily knowing the Python, like brushing up on whatever I barely remember from calc in college, there's still a lot that can be learned that makes me great at being tech adjacent or machine learning adjacent. And I think that's an underrated capacity that hiring managers may not account for, especially when they're early on hiring. So yeah, definitely a really great question from Chris. Our next question is from Mitchell regarding the concept of building infrastructure and data before anything else. If you're building from the ground up, how do you persuade businesses that when there isn't a concrete product already in place?
Maybe you don't. And that might be a controversial answer. If you have nothing in place, if you're a brand new startup, right? Sometimes the most important thing is getting something to market. That's why I said at the very end of the talk, this is all stuff that helps you burn down technical debt. Debt is a choice in many cases. Please don't extrapolate that statement to too far where we need to be. But like, you get to make decisions about when you incur debt. Just be aware that you're doing it, right? There's probably times where you don't want to do this. There are higher priorities and you need to get on those first. At other times, it becomes more of a negotiation with the business as a whole. And you're able to make I would hope you're able to make the case functionally that, hey, by investing here, long-term velocity not only increases, but it doesn't scale badly. Because as more intent comes in, as more technical debt comes in, the effort required to actually add new intent, to build new capabilities, to make business progress in the long term scales exponentially. It's certainly non-linearly, but I would say exponentially. Debt always has to get paid, and debt accumulates interest. If you're able to make those investments early, maybe not as the first thing if you're like a brand new startup or something along those lines, right? But if you're able to make those things early, or at least build them into your roadmap, that's probably a good choice.
No, it's funny, this question came up. We're actually doing this process right now here at Deep Learning.
Everyone
trying
goes
to
through
set up our infrastructure. We have a small amount of data. We have a small amount of, the models that we're using. And then we're like, hey, we should probably set up more infrastructure to enable us to scale much faster. So it's really, it's something that Andrew is pretty passionate about. So it's great to hear it from external voices as well. Our next question is interested in how much math, if any, you use in the industry versus machine learning or AI research.
So if you are an applied machine learning researcher, you are definitely going to be using math. If the question here was asked by someone who is hoping to not have to take a math class in college, you're going to take that math class, right? There's a couple of reasons for it. Like, one, you may not always need to be a perfect mathematician. I don't think that everyone's math skills need to be world-class necessarily, right? But I do think that having that mathematical background allows you to do a couple things. It gives you a good understanding of kind of the algorithmic choices that you will be making, lets you analyze the impacts of those algorithmic choices, and it allows you to contextualize a great deal of work. As a whole, It gives you the ability to more readily understand, interpret, and learn from much of the published literature that's out there. Like I said, do a lot of reading. I encourage people to do a lot of reading of papers. There's a wide variety of ideas out there. Not all of them are going to be helpful or applicable to the thing you're doing, but it increases your knowledge and exposure. Being mathematically fluent, at least, being able to speak that language will have benefits for you, regardless of where you end up inside of it. Everyone's experience is going to be different. You could ask me how much math I end up using. You could ask members of various teams that I've been on or different researchers. Everyone's going to tell you a different level of like, oh, this is what I actually use. I would wager that everyone will also tell you, yeah, it's very useful, especially as you continue to grow and evolve.
Sounds good. Next from Daniel, interested in what kind of practical problems you've encountered and how you fix them.
There is no way I'm going to have enough time in the rest of this presentation to be able to answer that in any level of satisfiability. There's a lot, right? As you build things out, especially if you're building them out as a part of a larger problem or a complex domain, there's tons of stuff. Personally, things I remember a lot from dealing with challenges around my data. A lot of the domains I've worked in have really challenging data requirements, especially if they're an adversarial domain where you really can't trust your data. So like there's a lot of that stuff that I remember very deeply. Bringing models to production is an interesting process from a process and organizational standpoint. Making sure your model is doing what you think it's doing. All of these are interesting. I'd love to go into that one deeper, but like that is a deep dive talk in its own respect. Yeah, it's big.
For sure. Next is from Don. If you were starting a small machine learning team, say a couple people, in a company that is inexperienced in machine learning, what aspects would you focus on first?
I would give you a
little bit about.
Go ahead.
Go ahead.
Oh,
you mentioned a little bit about how you have the ability to, focus on delivering a key need first.
I think that if you're a small ML team in a company that's inexperienced in ML, the very first thing you do is make sure you have a problem that machine learning can solve, 1, then follow that immediately with 2, make sure that your problem is sufficiently well articulated that you know what success looks like. Ideally, success looks like in a form of some kind of some kind of numerically measurable success metric, right? If your goal, for example, is, say, fix cybersecurity, that is a terrible articulation. Do not start building models if that is the only articulation you have for that problem. It's too broad. It's not objective. You can't measure it in any meaningful capacity. If your objective, however, is something like let's say you're in like the fashion industry or something like that, and your objective is instead make sure that customers who come in looking for a shirt get the correct size shirt 90% of the time as measured through NPS or some other methodology you want to use, that's much better. My example was terrible, but like that articulation is at least closer to knowing what success looks like. The thing I would advise to everyone starting a machine learning project is have clear, articulatable, as close to objective as you can get definitions for how you know whether or not you succeeded. Most important thing. Everything else flows from that. And at that point, you can invest in all the technical stuff, infrastructure, data, et cetera, et cetera.
And I would add to that, it's also about bringing in the sufficient stakeholders in the beginning, right?
Oh,
it's like the people who are eventually going to use the model, making sure that they're part of determining what success is, because you might think it's, say, NPS, and they think it's, no, I don't really care about NPS this time. I care about
something else.
You
can't define it. You can't define it in a vacuum. And like an experience that I have had is talking with stakeholders and realizing that like they went into that conversation with not like a non-technical understanding of what machine learning is, what it can do, how you measure it. They feel like it's magic in some cases, which is not a slight on them. It's like if you meet something new for the first time, you don't know how to think about it, right? And one of the things
sufficiently advanced technology is magic.
That's very true. And like one of the things I found is that when you ask them these questions, every once in a while, you'll get someone who starts saying something, stops and says, wait, I'm justifying what I do. Like I'm rationalizing what I do, but it's not actually how I know that I've solved this problem. If you're an analyst or something, you often say, oh, well, this is how I know if something's good or bad or whatever. You'll meet analysts who will start saying, well, I do this, this, this. And they stop and go, wait a minute, I'm explaining my steps. I'm not actually telling you how I make the decision. And then they'll stop for a moment and they go, I guess I just know it when I see it. And that is an insight that hits you like a ray of lightning, like a ray of light, like a bolt of lightning, because then you realize, oh man, sometimes humans don't know how we can measure whether or not we've succeeded in the stuff we do every day. And so having that conversation, sometimes your stakeholder doesn't even know what success looks like. And that can turn into an incredibly impactful conversation because you work on it together.
Yeah, no. And then that brings us back to your point about joint teams, that, you know, it really takes multiple hands, multiple modalities of experience in order to be able to, whether it's from the technical side, the data engineering side, machine learning, you know, and as well as business stakeholders to really make an algorithm work. That is unfortunately all the time we have left today. I know we're going to have to bring you back to teach us a little bit more. But for everyone that joined in Slido and asked questions, thank you all for the great questions. We wish we had more time to answer all of them. Thank you again, Zach, for joining us today. This brings us to the end of today's event. We hope you've enjoyed it. We're going to send a follow-up email with a survey for all of our attendees today. We'd love to hear about how we can make our future events better. The idea for AI Access actually came from a handful of responses that we received. And so, as you can see, we're very excited about the knowledge that our speakers are sharing. So please do reach out. We're giving out a 50% discount code for any of our online courses to up to 200 people who submit qualifying responses. So please keep an eye out, make sure to send in your feedback. And if you don't want to miss any of these future events, sign up via the link in the description box below for this and any other previous AI Access videos that you've missed. Don't worry if you can't make a live event, you can always find the recordings on our YouTube channel. We look forward